Right. Now we are Okay, good evening, friends. We have gone live on the YouTube channel of PRL. So this is a great evening for all of us here that we have a public lecture by none other than Nobel laureate Michel, and who's going to talk to us on other worlds in the cosmos. So before we start the session, let me invite Professor Abhijit to chair the session along with Professor Pepe, who is going to tell you a little bit more about Michel before he actually starts giving his lecture. So first, over to Abhijit.
Thank you, Professor Anil Bharadwaj. It's my pleasure and honor to, introduce Professor Michel Mayor, Nobel laureate. And I knew Professor Michel Mayor since 2007 when we accidentally met in Athens airport in Greece. And as we started, we were just sitting side by side actually. And as we started talking, and I realized I am talking to none other the person than the first discoverer of the exoplanet. And I was very excited. Then slowly, we evolved a very good friendship. And pretty soon I was invited in Genoa Observatory. And from there we started, we have a very good, positive collaboration between PRL and Genoa Observatory. And so with this very brief, small introduction, I would like to invite Professor Francisco Pepe, who is actually the instrument builder for Professor Michel Mayor. And we are very lucky that he is also here, and he is currently the director of Genoa Observatory. So I invite Professor Pepe here to introduce us, Michel Mayor, in a little bit more detail.
Thank you, Abhijit. It's an extreme pleasure and honor to introduce and welcome Michel Mayor here in Ahmedabad. And please allow me also to welcome Françoise Mayor, his wife, who joined for this trip to Ahmedabad and is actually accompanying him during his lifetime journey. Why is it a honor and a pleasure, especially a honor? Because Michel is my predecessor at the Geneva Observatory, but is also the person I worked with. I was under his advisory when I arrived at the Geneva Observatory. And it was really an experience to me, which I wish everybody, all the young people here could have, to work with this person. Not because it's a Nobel laureate, because he was not yet a Nobel laureate at that time, but because he's just an outstanding scientist. And he's driven by curiosity. And this is really at the level that I rarely have seen. And this is really the exceptional part. But in addition to that, it's not a person, an excellent scientist. He is not an excellent scientist and this extreme curiosity, but he's also a nice person, I would say a normal person, but in the positive sense, of which has been inspiring to me, together with his wife, also as a person. So being Nobel laureate and being a wonderful person is not incompatible at all. and Michel is the demonstration for that, and Françoise together with him. So sometimes, as seen from outside, one has the feeling that a Nobel Prize, especially if you don't know the people, that the Nobel Prize is something like winning a lottery. Okay, and there is a little bit of chance and so on, for sure, okay. But if you go then into detail, then you see that there is much, much more into this. And if you look at the reason, the rationale why Michel Mayor and Didier Queloz at that time got the Nobel Prize for Physics, is because they contributed, that was the statement, they contributed to change our view on the universe and the place, on understanding the place of our Earth in the universe. Okay, that's what, it was not only because of a single detection or a single discovery. It's because this discovery contributed to a completely change of view. And that was the main reason. And how did this happen? So the discovery of 51 Pegasi happened in 1995, okay? And this was an end point and a starting point at the same time. The end point of a whole, let's say, development of the research and also instrumentation. Michel has done a major contribution in developing instrumentation and techniques that were more and more precise and that eventually allowed to do this discovery. Okay, without this work, 51 Pegasi would never have been discovered. Pegasi B, sorry, the planet. There is also another aspect is that this planet was completely different from what was expected at that time. A big planet, almost like Jupiter, but very close to the star, unlike planets in our solar system. In order to find this planet, it was not sufficient just to have the best instrument. You needed also to be open-minded to expect this. And this as well had been prepared by Michel. It had been prepared by looking for binary stars and then companions to stars of even lower and lower mass, and eventually arriving at 51 Pegasi. And that was the end point of this development. But it was also a starting point because the domain of exoplanets didn't exist before. There were no exoplanets, so there was no exoplanet research. So he was really the one who started with this discovery, the new domain, and he continued the development. Abhijit told you that I built the instrument for Michel, but I mean, he was the person who inspired, who had the vision that we needed such a precise instrument to go even to lower masses. All other people were saying, no, there is no need to go for better precision because the star is limiting the measurement. So there is no need. Michel thought differently. So he is the person who initiated the development of this new generation of extreme precision radio velocity spectrograph with HARPS, and then this continued with espresso even better, with the near infrared. So it is all issued from that. And not only transit missions, they were inspired by the discovery. So, okay, so first Corot, Kepler from ground, now TESS, and later on Plato. You will hear about Plato in Stefan Udry's talk tomorrow. So all these developed from there. There is the Swiss satellite Cheops producing beautiful results and many more examples. So, as I said, Michel is, I think, at the origin of this fascinating new domain, and I will leave now the floor to Michel Mayor, Nobel laureate, to present you this fantastic universe of other worlds. And I thank you, and I invite Michel to join.
Okay. It's complex instrumentation. So this night, I would like to say a few words about the discovery of exoplanet. But I would like to start first from very old time. We are not the first one to have this kind of interest for this. Yes. it's very amazing to see that already more than 2,000 years ago, the Greek philosopher was already discussing the question of what is called in the time the plurality of worlds. It was not planet orbiting stars. It was a more philosophical questions. And in a very famous letter written more than 2,000 years ago by Epicurus, in the second part of the same sentence, letter, he mentioned living species, plants, and all other visible things could exist in some worlds and could not in others. It's incredible because we have proved the first part of this letter, but not the second one. The second one are for young people in the room to prove it. And in fact, this letter still exists, but we have also mentioned that philosopher much before was already discussing this question, but we still not have the original text of these people. And no, if I will arrive to a time, I have to do some big jump. This is a very nice atlas produced in the 18th century. And you see this evidently the solar system. Oh, no. The solar system here occupy a large fraction of the universe at that time, but already I have to. Okay, you can see the distant stars here, but already these stars are mentioned for some of them. If this is an enlarged view of this, you can see that they already have planetary system. So the general public was already comfortable with the idea that other planetary systems could exist in other parts of the Milky Way. But what happened later? Okay, now we are arriving to a time, and here probably you know that we are one star among 200 billion stars in a very large system called the Milky Way. It's very big. I will not give too much quantity, but okay, we have to keep in mind that the light will need 100,000 years to go through here. So the light needs only 8 minutes to go from the Earth to the Sun. So you see, it's absolutely without any comparison to the size of the solar system. And this is called the Milky Way. I hope you have seen it. So if we take a modern big telescope and you look a very small, a very tiny fraction of the Milky Way in the central part of the Milky Way, and you can see this huge number of stars like a sun. So the question, do we have planetary system orbiting this star here, this star here, and so on? Do we have the techniques, the instrumentation able to find planets? And it's very strange. You see that in the antiquity, in the 18th century and so on, people was very comfortable with the idea that we have other planetary systems in the Milky Way. But if you look the work made by very famous astronomers of the beginning of the 20th century, you see this is the logarithmic scale of the number of expected planets in the Milky Way. And you have 13, Shapley, this was in Cambridge, Shapley in Harvard, and so on. And you see the year 1915, so the part of the 20th century. And you see that this is 0, this is 100, 10,000. And you see all the estimation made during the first part of the 20th century that it was nothing. It was believed, due to a wrong theory, that the solar system was unique in the Milky Way. It looks crazy to see this already. And the idea changed drastically. I will describe why. in the middle of the 20th century because they changed the theory how to produce planetary system, and suddenly all the estimation jumped to billion, 100 billions of planetary system. And today, the observation confirms that we are really at this level. So we can say the most simple affirmation we can do is every star should have planetary system. Okay, maybe few exceptions. Okay, what are the reasons of this wrong? Already from the 18th century, Kant and Laplace, we understand, we need to explain the formation of the planets rotating in the disk, all in the same direction, need to have been formed from a nebulous or a cloud form orbiting around the star. And we do not have any believing how to produce such a disk of dust and gas. And the theory up to the middle of the last century was that you need to have the cross with an impact of two stars with close distance. So the interaction of two stars will pick part of the envelope of one and form a disk. And this was the origin of planetary system. But you can calculate, estimate the probability of such an event at zero. Billion of years, billion of stars, zero probability of. So this is a very nice example to see the distance between stars. Most of the universe is really empty. So what is the reason of the jump here? It's, in fact, we have one very small letter produced by, I will mention after, by US astronomer, giving the good thinking, the good highlights to explain what is it. To form a nebulous, in fact, this is an automatic byproduct of the formation of stars. The idea is very simple. If you have a very big cloud of gas and you have a contraction forming a planet, so always you have turbulence. So at some moment you have too fast rotation of the gas around the star. And this cannot be accreted by the star itself. So you need to form a disk of gas. But this apparently, this very simple idea was not taken into account during the first part of the century. And small problem. Yes, this is just few sentences taken from this paper. It's the name of this man is Otto Struve, and he did a very simple remark. Sometimes in science, the ideas are very simple at the beginning. You see, normally, when you contract a gas to form a planet, a star, or a planet, always you have a large excess of rotation, angular momentum. And so Struve was measuring low mass stars like the sun, and he realized that these stars are very slowly rotating. So we are expecting extremely fast rotators, and the sun and others are not rotating. And he said correctly, because the excess of angular momentum was used to form this nebula, the disk of gas and dust. And it was a very two-page letter, and this was the reason of the move in the estimation of the number of planets in the. Yes, just to have an idea, it's a very complex problem. The formation of stars is terrible. You have huge contrast of density between different parts. You have turbulence, you have magnetic field, and so on. And this is the region where you have formation of new generation of stars with some disk. And this is a nursery to form new generation of stars and planets. And you can see these big clouds, and maybe some of them have already observed this kind of cloud, because we can see with a good binoculars the Orion Nebula, and this is one of the closest clouds we can see. It's big cloud. It's 1,000 times the mass of the sun. It's a really big cloud. And this, if you are looking at a different galaxy, we cannot go out of our own Milky Way to take the picture. So this is a similar galaxy to our own one, spiral galaxies, and you can see all these pink dots are not stars, but huge piece of gas, and with forming new generation of stars, new generation of planets. This is the Orion Nebula, and already in the 70s, few colleagues was interested. This was the beginning of the infrared astronomy, and they looked the luminosity of young stars. And what they have discovered, that if this is a luminosity, the luminosity as function of the frequency of the luminosity of the light emitted, and this is the part due to the star itself. But you see that you have a huge excess in the infrared, and this is a signature, the emissivity of the gas of this nebula. So this was the first observations showing that really we have a disk of matter orbiting stars, young stars. After this will disappear. And if you like to have more direct observations, you can see this beautiful observation made by the Hubble telescope in 1995. And this is the Orion Nebula. And the Hubble Space Telescope was observing few stars emerging out of the cloud. And when you are looking with a high optical resolution of the Hubble telescope, you see all young stars are surrounded by a disk of dust and gas. So this was really the direct proof of the small letter made by Otto Struve. So here, this is the nursery of a planetary system. And the direct conclusion that planetary system is a normal byproduct of the formation of stars. So we should expect that we should have a huge number, billion of planetary systems. So, go back to our questions. This is a small field you see of the Milky Way, and you see that we can detect orbiting planets also. This is, we have a big difficulty because the luminosity is made by the sun, but the planets are only reflected a small piece of the luminosity coming from the star. So the ratio is absolutely terrific. Typically in the solar system, the ratio is visible of the luminosity of the sun and Jupiter is 1 billion. So let's imagine when you are looking a solar system at a planetary system at some distance, you are completely dominated by the luminosity of the star itself. So no way to, or extremely difficult to see the planet close to the star. So we are obliged to do indirect measurements. And for example, you see, this is the star, this is the planet. We cannot see the planet, but all the things are orbiting around the gravity center of the system. And eventually, as the mass of the star is much, much higher than the mass of the planet, in fact, this diagram is not at scale because the distance is much larger for the planet itself. So, but you see that if you design an instrument with a sensitivity to measure the change of the velocity of the star, you can see maybe that some stars will be approach you, recede, approach you, and so on. So if the star is doing something like this, it's for a good reason. You can do some simple calculation, and you can detect the period of the object. You can determine the amplitude, the shape of the orbit, and you can have an estimation of the mass. So you cannot see directly the planet, but infer the existence of the planet by this. So the technique is simply to use a spectrograph and try to see changes of the frequency emitted. And once again, it's not like this, because due to the small mass of the planet, the change of the position of the line is actually terrifically small. It's happily we have the huge help of the nature that you have dozens of thousands of atomic transitions, and this in the spectra, and you can detect this small change of this forest of atomic transitions. So after it's a part of techniques to build the instrument with the sensitivity to do it. And we did this, okay, this idea was already proposed a long time ago, but at the time where it was completely impossible to dream to have sensitivity to the disease. But the idea was already existing. So we built with our colleague from the south of France, he has developed a new kind of spectrograph, and we started a huge program in 93, 94 to search for planets, because this instrument was just at the level of the sensitivity to ask these kind of questions. And after relatively, we have selected a sample of 142 solar type stars, and it was boring. You measure the velocity of the star, another star, another star, another star, and the next night you repeat, measure the star, and 1 month after you and it's only when you have collected a long series of measurements, then suddenly you see that you have some periodic system. So it's not a discovery made one night. It's only when you analyze a series of data. And okay, a lot of them was with some variable star, but most of them looks not really periodic. And we understood later on the reason. It was because it was related to magnetic activity in the atmosphere of stars. And this is a very serious problem today, still today. But one star, its first small name is 51 PEG, show exactly what we are expecting. It's moving periodically like this. Now this is the original measurement. When we have the first in, it was only 12 measurements. This was just when we published the measurement. So this is 30-something measurement. Okay, everything looks fine, except that the estimated mass was half the mass of Jupiter. Okay. But the theory said that to form a giant planet like Jupiter, you need to agglomerate first silicates and metals, and only after to have the mass large enough to agglomerate ice particles. And ice particles exist only at some distance of the star. So you cannot explain the formation of giant planets close to the star. And here it's only 4 days. So let's imagine a giant planet Jupiter orbiting so close to the star. So it was completely in disagreement with the theory by a factor 1,000, because the theory says some more than 10 years, and we have fallen. So we did some tests. We wait 1 year, repeat the measurement to be sure that the phenomena was still there, and so on. And after being convinced that we have published it, and today more than 5,000 planets have been discovered by different techniques, by different teams, and so on. So today it's a huge business with thousands of people, and some people in Ahmedabad. or Monda. I will discuss after. So I will just say a few words of the physics. Why it is possible to have a Jupiter-type planet so close to the star? What is the mechanism to form this? And in fact, it's very strange. It was a mechanism already studied 15 years before, but nobody realized that it was really to be taken into account for the theory of the formation of planets. But it was, this kind of work was already made by very prominent colleagues, in the 80s. But it's only after the discovery of 51 PEG that people realize that, yes, this is a very basic phenomena to be taken into account to explain the formation of planetary systems. And the idea, I will not detail too much, but when you have the formation of a new planet here, this planet will accrete, will take the matter in some part of the disk, but after the mass of the planet will induce some perturbation in the disk, and this perturbation will react on the orbit of the star, the planet itself, and the net result, it's a complicated calculation. And the net will be thinking of the orbit, and starting from maybe 5 times the mass, the distance of the Earth to the Sun, you will do a spiraling like this. And after, it's a different story. Why it stop and not be engulfed in the star, it's a different story. You can study it, it's interesting. So, completely different story. A consortium of many countries, US, Europe, Japan, put the money to build the same instrumentation. It was an interferometer. It's a combination of 60 dishes of 12 meters on the Atacama Desert. In fact, on the Altiplano in the under South American Chile. So when you have all these dishes are observing at the same time the same object, but after you collect the luminosity received by all these dishes, you do some clever analysis of the data, and you have an absolutely fantastic spatial resolution. So you can see extremely small details. And it's absolutely beautiful at 5,000 meters in the under. So it was known that, for example, this is a normal astronomical picture with a small cloud here, where we knew that we have 2 young stars inside. So some colleagues look with these 60 dishes at the same time and analyze the shape of this kind of young stars. And what they discovered, that the young stars was here, another one was here, and when you, with a high spatial resolution, angular resolution of the interferometer, the result is exactly what we are expecting from the theory, not due to the formation of one star, one planet, but the formation of full planetary system. So this is the birth of a planetary system. And this was absolutely incredible to see the progress made in few years. And evidently this colleague was extremely excited to continue this kind of study. And you see a lot of series of young stars, and all, or almost all stars, have this kind of shape with difference because it depends on the mass and so on. The detailed change, but you have the formation of planetary system. Going back to our own business, so after the discovery in south of France of 51 PEG and few others, in the northern sky. Okay, we moved to southern sky for observations, and we have developed a new instrument, you know, paper from Francisco, 20 years ago, and we put this new instrument. Okay, we capitalize on what we can improve, what we can do better, and so on. So the net result was that we achieved a precision of 1 meter per second. This was contractual. We have signed a contract with ESO, the European Observatory, to achieve an instrument with 1 meter per second. We were a little bit naive to be sure it will be possible. In fact, it works, and we receive quite a lot of nights on a 3.6 meter telescope in Chile. So 500 nights on a big telescope, and this is the telescope is inside this dome. This is the spectrograph before closing the vacuum tank, and this year we have made some celebration of the 20th anniversary of this. Okay, just to see that the shift of the wavelength, 0.3 meters per second, correspond to a billionth of the wavelength. So this is much not like we have shown here. It's really a very small shift. This is technical aspect. So how we are really doing to find planets. So as I said, we measure the velocity of one star, and after during 1 week, we repeat the measurements, and after 1 or 2 months later, and after the year after, and so on and so on. So this is the velocity versus time. And you see at the beginning, oh, it's strange, it's strange. And then after you say, oh, maybe we have a planet. But then after we go, you see every step of measurements here correspond to 1 year of measurement. So we are measuring a lot of other stars because we don't know a priori what to do, and so on and so on. And you see 1, 2, 3, 4, 5, 6, 7, 8, 9, 8 years. And at the end, you have all these collection of measurements, and you let the computer to fit what he believes to be the best. And the best is 3 planets. 3 planets with the mass approximately of Uranus or something like this. So this was the first system with 3 planets of this kind of mass, 10 times the mass of Uranus. So this is typical of what I will not show the 5,000. Don't be afraid. Okay, today, something more than 5,000 planets or planetary systems. Why we are continuing to measure? Well, we have so many. What is the reason to continue? In fact, that we have discovered a huge, huge diversity. The solar system is absolutely not a typical example of what we observe. For example, we have some period as short as few hours. You have planets orbiting in few hours the star. You have some planets with less than that of the Earth, but some are much, much, much bigger. You have some, okay, in the solar system, all the big planets are almost of circular orbit. We have some examples with orbit like this, with a huge eccentricity. You are, okay, we already are detecting a lot of multiplanetary systems. You have, okay, in the solar system, you have the sun here, and all the orbits are almost in the ecliptic, in the plane. But here, and this is perpendicular to, almost perpendicular to the rotation of the sun. But here, we have discovered that sometimes the star is rotating like this, but the orbit of the planet is like this. And worse, in some cases, we have planets orbiting in the opposite direction. You see, understanding the formation of planetary system is maybe a little more complicated than we are expecting before. And more, evidently, this is a complexity of structure, but you have the same complexity of composition. You have When you have a planet, rocky planet, close to the star, it could be only a lava planet, but the temperature is above the melting of the silicate. You have also ocean planet made mostly from water, not a small ocean like we have, but big ocean, 600 kilometers and things like that. So it's very, very, very interesting to understand the complexity. And this is part of the reason why we continue to explore this complexity. Okay, I'll describe the indirect detection of planets using the Doppler effect. But as we have detected so many planets with short period, immediately you say, oh, if you have a short period, you have a probability that the planet will cross the disk in between your telescope and the star. So this is a good condition for what we call an eclipse. In the present situation, we speak about planetary transit. So, and we cannot see the planet, but what we can observe is a small dip of the luminosity, periodic dip of the luminosity. And the probabilities for 51 peg is something like 5% that the inclination of the disk is convenient. And this was a great idea because this was at the origin of many, many experiments providing a huge number of planetary systems. And this, we have detected a star with a period as short as 3.5 days. Well, a little bit closer to the star itself than 51 peg. And we collaborate with colleagues in the US at Boulder, and it's not a big telescope. This is a 10-centimeter telescope in a garage of belonging to Tim Brown. And exactly at the moment predicted from the Doppler effect, you can observe the dip of the luminosity. So you remember your school exercise. If you have the mass of a sphere and the size of the sphere, what is the mean density of the sphere? So I'd like you to remember these things. And if you do the experiment, you see the mean density of that planet was 0.3 gram per cubic centimeter. So it's a third of the density of the water. So this was a direct proof that it was not a completely crazy object, but it was really a gaseous planet. And our colleagues have repeated the measurement the year after by using the Hubble Space Telescope above the Earth's atmosphere. And you see the quality you have by doing incredible, incredible. So immediately, this is a Jupiter-type planet. So Jupiter is 300 times the mass of the Earth. So you see, if you are something much smaller, 100 times smaller or less, in fact, we still have the possibility to detect the transit of an Earth-type planet. So this is the idea at the base of many space missions. And we have one first, CORO, a small telescope having provided few first planets by this technique, it's a space. And after you have the largest mission, Kepler, it's about 1 meter telescope. And once again, the idea is absolutely simple. You have the star like this. You build a satellite, and you look always in the same direction. Many years, you continue, and every few minutes, you are doing a picture, a slide, or no, picture, a photography of this part of the sky. And you have you select a piece of the sky with something more than 100,000 stars. So at the end of the process, you have 100,000 light curves. And you look with the computer, And sometimes you see something like this. But sometimes you see something more complicated. So because you have 2 planets, or 3 planets, or 4 planets, or 5 planets, and so on. And this is quite not frequent because a priori you need to have a disk very common to all the orbits, like almost like we have in the solar system. But so I would say that you miss most of the planet. Every time the plane is like this, you cannot see anything, but you have planet. So you have to correct for the probability of things like this. But you see here, this plot is the radius of the planet detected versus the period, no, the radius versus the period. So 1 Earth will be 365 days and 1 mass. It should be here. If you have a planet with 10 days, with 1 Earth, mass of the Earth, it will be here. 51 peg will be 4 days, something like this, but something like here, and so on. Okay, every time you find a planet with star with 1 planet, you put a dot, black dot. When you have 2 planets, you use this color. 3 planets, 4 planets, 5 planets, 6 planets. You see, it's very common. It's absolutely common to have multi-planetary systems. And you can ask me why you have no planet here. It's only a question of sensitivity of the detection. A small deep arriving every 2 or 3 years is much more difficult to do. So this is for the future. Now, going back to Doppler spectroscopy. And so Francesco Pepe was the PI of the development of a much more ambitious instrument, collecting the luminosity of the 4 8-meter telescope. Underground, you have a set of mirrors collecting all the luminosity, and it is equivalent to 1 telescope of 16 meters. Because that's good. And so you receive so large number of photons. So to observe this very fine planet, it's very useful. We will see why we need a lot of photons. So this instrument was designed and to achieve a precision, and it showed it was achieved, a precision of 10 centimeters per second. And this is typically what we need to detect Earth-type planets. And evidently, this instrument can do many, many other things, evidently, not only planet detection. But we are not alone. You have, I don't know, five instruments in the world with the capability to measure velocities below 1 meter per second. Have you seen that first you have satellites providing targets by thousands. You have test satellite providing targets on very close stars. So the most interesting one, because we can have much more type of experiment with this close stars. So, and in the future, the series of satellites will continue, and you will have in a few years plateau, and it will be described by Stefan Usry tomorrow. And this is still more ambitious mission to have the capability to analyze the vibration of stars, to measure the mass, the age, and the star, etc. So the story is not finished, and so you have enough stars to provide material to people in Montagu, in Chile, and so on. So welcome to this expert. And this interest started many years ago. And at the beginning was one spectrograph was developed on a 1.2 meter telescope on Mount Abu. And already they have detected several planets. But evidently, always like we have made ourselves, you can see what is not what are the limiting factor in the precision. So our colleague here in Ahmedabad have developed a second spectrograph providing a much higher precision. It's called PARAS-2 and also installed in Mount Abu on a telescope of 2.5 meter telescope with I would say, the extreme precision of 0.3 meters per second. This is typically the best we can do. At some, for this, okay, you have one maybe at 0.1, but you need a much larger telescope size because you need a lot of photons and so on. So, okay, this is interesting for astrophysicists. But what is most interesting topics for most of the people is, do we have life on some of these planets? So this is the next step in the interest of people working in the field. Do we have the capability to search life for some form of life on some of these planets? So Earth twin, do we have the possibility to detect this small planet? Like, and the most important question behind this is life a unique phenomena having appeared on this Earth, on this planet, or is it some kind of very common process in the development of the universe? And it is the Nobel Prize, Christian Dedoux, a biologist, used the term a cosmic imperative. It's the fact that you start in the life of the universe by soup of particles, and then after, inside the stars, you form atoms, and then after, when the temperature is not too big, you form molecules, and so on, is simply the continuation of these seconds of complexity. And we don't know. So do we have the possibility to answer to this question? So, difficulties. After the philosophy, difficult. This is a real image of the sun. At the same scale, you have Jupiter, Saturn, Uranus, Neptune, and here in the small box, the Earth is here. Let's imagine the Earth is so small. Then, and we, for different reasons, we are interested in this kind of planet, rocky planet here. And if you are looking for the reflex motion, the Doppler effect, let's imagine this small piece, what you will disturb the motion of the sun. Second difficulty, if you imagine that this planet will cross the disk with all this magnetic activity and so on, and it's only 10 minutes 4. It's a teeny small dip in the luminosity. So, okay, it's not so easy to find rocky planets. And why we are interested in rocky planets? Because this corresponds to one of the most basic criteria of life. When you have a very small living space, let's say one single cell, it has to protect himself from the surrounding, but also he has to, it's already a very complex system to exchange energy, nutriment, and so on with the surrounding. Okay, this is the basic form, constraint of a very simple form of life. But to have an additional one is the fact that you have to transfer all this information to your daughter. At every generation, you have to transfer the information. So life is one of the basic characteristics. Right? is the transfer of information from one generation to another. And we have one example, is the DNA. You code everything to survive, and to transfer this information to a descendant is coded in a long chain of atoms, the DNA. And if you eat the DNA above a little bit more than 100 Celsius centigrade, the chain breaks. And this is what you are doing every day when you cook elements to avoid the bacteria. So we are killing the transmission of life. If you cool your food below -20, the chemical development is so slow that nothing continues to be developed. So this constraint to find rocky planet with a temperature equivalent above to the temperature of life or of water is not a fantasy. It's simply a consequence of the physics and the chemistry. And then the next step, why water? Because water is a solvent for chemical reaction, absolutely fantastic. So it's the reason why astronomers are fascinating to find rocky planet with liquid water on the top. And the idea, if life develops itself, is to try to analyze the chemical composition of the atmosphere of the planet, not of star, to find some kind of molecule related to the development of life, and maybe having polluted the atmosphere. So this is not to go and see some form of life, completely impossible, but simply analyzing the chemical composition of the atmosphere. All these ideas start from the remarks made 40 years ago that the atmosphere of the Earth is dominated by oxygen, and oxygen is a very active element to form links or chemical reaction with rocks. So people say, oh, maybe the existence of 20% of oxygen in the Earth's atmosphere is maybe what is called a signature of life. Okay, no, maybe the story is a little bit more complex, but this was the idea to find what's called biomarker. So to do this, you need a lot of photons, because I will explain how we have a chance. I said before that the ratio of luminosity between the star and the planet is terrific. But we have one chance, beautiful. Sometimes we have to take this opportunity. And you will understand why we need a lot of photons. Here, this is the problem. Maybe you have heard about the exceptional telescope when I was young. The Hale telescope at Montpellier with a diameter of 5 meters. What? It was really the flagship. And today, okay, this corresponds to all the projects made. Here you have the 4 telescopes for Paranal, 4 8-meter telescope. And this is the telescope in construction in north of Chile with a 39 meter of diameter. So you cannot put the primary in this room. It's big. Okay, it's not one single piece. It's a set of many, many small hexagons. So this is not long-term. This is wrong. It's 225. Okay, but nevertheless, it's not too far from right now. And this is, it will be anything in astrophysics, but in particular, be devoted part of the time for exoplanets. This is not the last one. This was in June last year. You see that all the enclosure, the dome is already in good shape. And apparently, right now, the last images we can have, I don't have, it's already like, yeah. So you see some typical, I don't know. Yes, you can see a valve here. As you see, it's absolutely incredible. And eventually, also in a very beautiful place, beautiful in terms of for astronomers. It's extremely dry, 2,800 meters, except one point. It's extremely close to the Atacama Fault, one of the most active places in terms of seismology. And but it's fascinating for engineers. It's a gift because they have to build such a thing to take into account the risk of a class 8 or 9 earthquake. And it's a okay, I don't know what will be the result. We have to wait. But for example, they have sensor a few kilometers, and when you have a surface wave arriving, they have the time to send a message to the telescope to increase the distance between pieces of material where you have to erode the contact of matter. You have airbag and so on and so on. So I don't know. At La Silla, it works. At La Silla, it's not so risky, but it works. You have some airbag to avoid the mirror do something like this during the earthquake. So, okay, we'll see the results. But we cannot avoid to speak on the small telescope to compare to the ELT. It's 6.5 meters, but in space. So this is the James Webb telescope, fascinating instrument, put in space, with the advantage to be out of the Earth's atmosphere, and the capability to observe in the infrared. So here, this is a complex view of the mass versus period of the planet detected by different techniques, the transit, the radioversities, the indirect imaging for the very distant planet, and so on. And Earth-type planet was at this level here, and the giant planet, Jupiter-type planet are here, and so on. Cold Jupiter, like Earth, hot Jupiter, like 51 Peg, mini Neptune, rocky planet here. And this group of people, having provided these slides, say, oh, it will be interesting to analyze this kind of exoplanet, rocky, temperate, because the real Earth will be here. So it will be interesting. And so the James Webb will do a lot of things in the future to analyze the subject. What we can do, it's very simple and maybe one of the most exciting things for the future. Let him, you have seen, the deep of the luminosity of star depend of the size of the planet and the size in a specific wavelength. If you observe the Earth in the visible, it corresponds to a radius of something like 6,000 kilometers. Let's imagine you repeat the measurement in the infrared, in the domain of the ozone. Ozone is completely blocked at something like 40 kilometers. So the radius of the Earth, seen in the infrared at 9.7 micron, looks a little bit bigger. So if you analyze a series of transits in different colors, you can measure the opacity of the atmosphere at different frequencies. So you can, for free, nature provides you a spectrum. You can analyze the chemical composition of planet only looking the depth, the contrast of the different transits. And this is a huge, huge interest. And doing this, you see, you change the color and you see, okay, it's not like this. It's much, much, much smaller. So this is a need to have a huge number of photons, big telescope, to see this small change of the, with the color, with wavelengths. And this is the measurement made last year, 2 years ago, by the James Webb telescope. And you see the set of transit in different colors. You see, okay, you have changed the form for different reasons, but if you analyze this, the contrast as a function of the, it's more smaller than what you can see here. You have the capability to analyze to build the spectrum of the planets, not the sun, but planet. And the result for one of these objects by the James Webb is, you see, this is the wavelength and the measurement of the transit depths, you see. And you see that this was the most first claim. It was due to carbon dioxide here, discovered immediately after the first measurement of the, and then after it's a combination of different kind of molecules. So eventually, if you want to increase the quality, you would like to increase the quality to see what are really due to this molecule or this one. So this is the idea of the future. I believe we can expect a huge amount of discoveries made by this technique here. And already they have interesting results on the quantity of elements compared to the solar system. So I will just finish my talk because you are angry. Just to do a completely different comment. So you can see in the literature, Star Wars, and so on, you have a huge, interesting, exciting story. Okay, I have nothing against, but it's not physics. You have seen the Milky Way is huge, 100,000 light years. Let's imagine in a study of every teams working in the field, we will discover a perfect Earth analog with water at the surface and everything fine, at let's say 30 light years. 30 light years is really, at the scale, a neighbor. It's really a neighbor. So, 50 years ago, Apollo 11 went to the moon in 3 days. The light needs 1 second to do it. 30 years correspond to 1 billion of seconds. So this neighbor is already 1 billion times further than the moon. So it's 1,000 times million and so on and so on. It's really complete. And okay, the light needs something like 30 years to come. But if you send, let's imagine, a spacecraft to go, it will need to accelerate and to travel and decelerate and so on. So at minimum, it will be 100 years at the velocity of light at the top. But it's impossible. Where you will find the energy to increase the kinetic energy to this light? Impossible, impossible. So I'm sorry to kill the dream of the fan of Star Trek, but we are living on the Earth, and I do not believe that we will emigrate to other planets there. We will only analyze the possibility of life, the sign of life, by analyzing the chemical composition of. Okay, sorry, but our life is, our planet is not so big. Yes, so nice. Yeah. So thank you so much. Uh, Secondly, I like to do a bullet at the end of the conference among you if you believe that life exists in other parts of the universe. Not like us, but one unicellular is already life. How many of you believe, if you believe that we can find in the future or a colleague working in the field, do you believe that life exists? Okay. And at the opposite, some of you do not believe that life exists in other parts of the universe. Oh. So, but be precise. I don't have any proof to say that some of you are right and some of you are. We have to search. The only way to do it. And in 20 years from now, maybe we will have an answer.
Be here. So I hope you all got illuminated by this wonderful talk. And before we take few questions from the audience, we would like to felicitate the Nobel laureate. And after that only, we'll take few questions, okay? So may I request Michel to come over here?
Wow.
Can I keep it here?
So with that, add one thought. Here, this is the public tool is even parallel to the total. I was to start with that and only very simple. Chemical composition in the atmosphere. So a lot of colleagues have done a lot of work behind all what I said.
Have to put it in the pocket.
I'm searching his pocket, how much money he has.
Merci.
Just be here.
Yeah.
Be here. So you all know that behind a successful man, there is always a woman. And we have with us Mrs. Michel Mayer. So my request, Mrs. Michel Mayer to come over the stage.
So kind.
Here, you would like to be here? Because we'll take some question answer. So it looks nice. अभी आप थोड़ा सा पीछे हो जाइए. Just be here. Just आप थोड़ा पीछे जाइए. Slightly. Yes. Yeah. Take. So now is the turn for the question answers. And now you can sit down properly. You want to- Oh, you want to- Okay, so want to come up? So now it's open for questions. Michel is ready to answer. And do we have a mic in the audience? Do we have a mic in the audience? Yeah.
Yes.
Mic
Yes,
दे दो
please.
audience को.
Mic दे दो उनको.
Hi, Professor Mayer. Extremely exciting talk, and I do hope we do find life in the universe. I'm going to ask a slightly sacrilegious question. So you mentioned about how we found all of these almost 5,000 plus exoplanets and well, exoplanets around other stars. So have we seen any systems where we find no planets around that star?
If you have seen what? No planet? Oh, I cannot understand, reply correctly to this question. Because, for example, let's imagine with the same instrumentation, we have observed the solar system. So Jupiter will be easily detected. 11 meters, 10 years or something. So it's easily in the capacity of the present instrumentation. Saturn is already not so evident. 30 years, 2 meters, 2.8 meters per second. Okay, we will have seen some drift, okay, but it's all. So if you have as a planetary system without a Jupiter, we will not have seen it. So you see, it's one of the reasons why we have started the systematic survey in the southern sky in 1998. So it's 25 years after, but we continue because every year we add new long period planets. So, but I believe the fact to have not detected something is absolutely nothing. Because if you have a small planet like Uranus with a long period, no way to detect it.
Thank you.
Okay. More hands up in the back.
For a long time, I had this question. I had asked Abhijit too once. So we are looking at stars with very large planets, very near to sun. So if we look at our solar system, there are models where we describe migration theory. So the Jupiter at a time T is sometime 4 billion years ago was very near to the sun. So are we looking at planetary systems that are young in time scales, or it is because of the time difference that we are looking at a different time interval?
Okay, I will try to answer. Okay, all these planetary entities are relatively close. So, okay, we have some example at maybe 100 light years or something like that. But most of them are 10, some decades, so 30 light years or something like that. Let's imagine you, with some fantastic photography, you take a picture of the Earth 30 years before. You already have living people, you have the forest, life, and so on. So the problem, very important in cosmology, the time lag, not a problem in the field of exoplanet. And the other question, why you are not observing very young? It's technically a problem of, because like for the people, young planets are very excited. So you have a lot of magnetic activity, you have variability and so on. So it's not the easiest object to be observed. What is called T2 stars have the luminosity changing a lot. It's difficult too, it's very difficult. Okay, some colleague try to do it, but not so easy.
Okay, so some hands from this side. There was something hands here on this side. No? Nobody's raising the hand here. There were some hands here. Yeah, this way. Right.
Hello, yeah, good evening, sir. Yeah, thanks for the exciting talk. I'm Orijit, working as a PDF here in PRL. Some of your slide you discussed about the biomarkers, various molecules detected in exosolar planetary atmosphere. So if you see the elements which is responsible for the biomarkers is carbon, hydrogen, nitrogen, oxygen. So some of your slides I am able to see any nitrogen containing molecules. So why is it so? Is nitrogen get depleted so much that it didn't form any molecules, or like the condition is so harsh that it didn't fall, or like there is no chemistry happening which enhance nitrogen forming molecule to grow there?
I mean, you are better placed than me to answer this question.
Nice one.
Can you repeat the question for my colleague?
You have one
So,
more mic over here.
Why there are very less nitrogen containing molecules? Nitrogen is also important for biomarkers, right? So I see only methane, but unable to see ammonia or NO2 kind of molecules.
Okay, I'm not quite sure why I got thrown under the bus here for this question, but so nitrogen is hard to observe directly, right? But ammonia is a potential signature that people do look for. So it's not true that we're not looking at nitrogen molecules. There are many nitrogen. HCN, hydrogen cyanide, actually tends to be a molecule that has a large signature. So indeed, there are nitrogen-containing molecules that get observed. But I still don't know why I got thrown under the bus here. So. Yep.
So if
Okay.
Thank you. Yep.
So any more hands here on this side? Yeah, it's here on this side. Can you just pass it on the mic?
Thank you, sir, for this.
Please
Such a
raise your
nice
hand higher up so that they can see it. Yes.
So I wanted to know that what makes difference between this single star and stars with planet? What is the what makes difference? Some stars have some no planet and some stars have some planets.
not sure to have understood the question.
So question is that what makes difference between a single star and a star with planets?
Okay, I don't know. I will try. What we have, maybe it's not a good answer to your question. What we have observed is a relation between the chemical composition of the stars and the number of detected planets. And not the number, the occurrence, the frequency of giant planets. So you have some relation between the chemical composition, because you have more material to form planets and so on. And this is, but after the detail to form, I don't see any papers relating the physics of the star, to the number and the structure of the planetary system. I'm not sure to answer correctly to the question. Maybe after we can discuss.
Good evening, sir. We saw in this presentation of yours that exoplanets have sometimes an inclined plane of orbit around their star. Why is that a peculiar feature worth mentioning? Because I find it really interesting that our solar system does not have any planets that have an inclined plane of orbit around the sun. So
Yes.
why is that the case?
Yes. Typically, the most probable reason of that is what is called the quasi effect. If you have one star here, you have one planet here, and you have a second star here, for instance, the gravitational influence of the other stars will induce some perturbation of the orbits, and this modifies the eccentricity and the inclination of the orbit. So if in some dramatic case, it can produce this kind of thing. So it's very strange. It was completely unexpected. We have observed this kind of phenomena many years ago. And all the first measurement we did showed something like boring situation. The star and the orbit of the planet exactly like we have here in the solar system. And suddenly, some measurement appear with orbits like this. The star is always like this, and few cases on the reverse. So this is typically of the complexity of the system. Don't forget that sometime at the formation of stars, they are part of multiple planetary. You have several stars, maybe 3, 4 stars linked in a small system, and they are not mechanically stable, dynamically stable. So sometimes one planet will be kicked out of the small system. So you have dramatic dynamical effect. So I'm not sure if this is the correct answer, but I believe this is the only way to explain.
So this can be also conspiracy theory, right? Conspiracy theory of the God making different inclinations.
Uh, Sorry. Hello, sir. My name is Kunal. My question to you is that since we know that the formation of a solar system or maybe a planetary system happens due to accretion of materials, and that's how a star and planets are formed. Can we say that the accretion of a star formation is not 100% efficient, and that leads to the formation of planets around it?
Okay, the accretion, the phenomena of the migration of the orbit and linked to accretion is an extremely efficient phenomena. And this is part of the reason why Goldreich and Treman do not put so much emphasis on this phenomena, because the time scale for the migration so efficient, so quick, that they say, oh no, it's incompatible with the existence of planetary system. So after the thing was more complicated, they found some way to stop and so on. Okay, but I don't know if can you repeat the paragraph?
Right. Okay. So what I'm trying to ask is the accretion of a star formation not 100% efficient, which leads to planetary formations around it, because the material could not reach to the accretion part of it, and which is why that led to the planetary formation.
No, I believe if you have a disk of dust and gas, you need this disk to form the planet. So you need accretion. I'm not sure to completely understand the point. I don't know if you can help me.
Go to the next question.
No, okay. No.
Just tell your name and from where you are.
Sometimes I have some difficulty
Hello?
to understand it.
Hello?
Yeah, I'm Namaskar and I'm a student from Mumbai. I just wanted to ask, we know that an atmosphere evolves as a planet evolves. Like, take for example, Earth, we didn't have oxygen first and now we do a lot of it. So I wanted to know that when you're looking at the atmospheric composition of certain planets, let's say rocky planets, can you find out whether it's like a protoplanet or has it evolved? Is there any way we can get that kind of information?
Oh, I believe this is a dream for the future because it's true. As I said, if we have some prediction of the estimation of the spectrum of the Earth's atmosphere at the very beginning, after the origin of the oxygen and so on, we have completely different kind of spectra. So it's true that this complicates the story. I believe this is very difficult domain to find. And I believe it's all the difficulty to find real significant biomarker, to be convinced that, because it's indirect detection. So at what point you are convinced that you cannot explain this by different way. But you know that this is completely new domain. I know here in India and more specifically in Ahmedabad, you have people working in exobiology. In a lot of places, you have a huge team of people. It's in the same institute, you have chemists, biologists, physicists, and so on, astronomers, yes. Also geologists and so on. They need, because the problem, the origin of life is not a simple question we can solve. Okay, yes, this is. No, it's a very complicated question. And I don't know, you have exobiology institute or network and things like this thing in many places. It's a nice question for the future. Young people do it.
Yes, they have to do it.
Yes, exactly.
Sir, sir, I'm Shumit from Bangladesh. I have a question for you. Is there any relation between small planet radius gap and planetary migration? Small planet radius gap, the scarcity of planet between 1.5 to 2 Earth's radius.
Yes, the problem of small planet, okay, you have the problem of detection, it's more difficult. And then after the theory of the migration is depend quite a lot of the mass of the planet. And it looks easy when I show this slide. But in fact, in detail, it's very complex, very difficult. And for example, you see small body have a very strong migration. And this is completely crazy because if you eliminate immediately all the small body, planetesimal, or you can form a planet. So you still have some work to do.
Thanks.
Yeah, over here.
Hello, sir. My name is Mayuri. It's an honor to actually have this lecture with you. My question might be very strange, but I just wanted to ask you, like, there are rogue planets which do not actually orbit around any stars, but they orbit around dense gas. So would these planets have some atmosphere that can maybe support life, if not evolve life on that planet?
What are planets? They are not linked to the star.
Ah, yes. Okay. A planetary system is some kind of BR, a game. You have several planets with interaction between them, and this was a very classical question of celestial mechanics. Are we sure that the solar system is stable? Are we sure that we will not lose some planets? So apparently, for the coming billion years, it's good. It's good. But not on the completely long term. We have some possibility. And this question exists for other planetary systems. And we are sure that in some cases at least, you will have some planet kick out of the system. And in some cases, you have what is called free floating planet. But if they are not illuminated by a star, difficult to detect them. Okay, at some moment, they will emit a little bit of infrared. And you have some claim in the literature. They've detected free-floating planet in a cluster, where you have very young object. I believe it's, okay, I disagree with my colleague at this point. Because this is very fundamental question. What is the upper mass for a planet? Okay, we have good example. We have planets more massive than 10 times the mass of Jupiter. Several planets orbiting, and so on, circular orbit and things like that. And you have also what is the minimum mass, the formation of a star. And if you trust the colleague having approached this question, it could be about 4 times the mass of Jupiter. So we start with a crazy situation where in the domain of mass, between few times the mass of Jupiter and maybe 15 times the mass of the other world, you don't know a priori if it's a planet or of a very low mass star. So personally, I believe that the free-floating object found in Orion by my colleague of Spain are very small brown bars. But, okay, I have not been to see if they have been formed. They are, okay, it's, okay, I have another argument. When you have this interaction of many planets in the disk, what are the most sensitive to the possibility to be kicked out of the field? Lightest one, the most massive one. It's much more difficult to so I believe, and these objects are several Jupiter. So I don't believe it is real planet. They are in the domain of mass of planet, but they are formed by collapse of matter like stars. I don't know, maybe. Okay.
Good evening, sir. I'm Aditya Das from Planetary Science Division, BRL. So I have a simple question. So if we are to look at the solar system based on the current technology that we have, would we be able to detect any planets?
It depends. If you are using Doppler shift, Doppler technique, the Doppler spectroscopy, we can detect Jupiter, Saturn, nothing more.
Okay.
Okay, in the future, maybe it will be another one. But for the moment, I don't see we have the instrumentation to detect the Doppler effect of Earth-type planet. Okay, comment dire? The modern spectrograph with the possibility espresso to measure 10 centimeters per second looks appropriate for that, but is without taking into account the magnetic activity of the star. So I believe it's still not positive. Transit, yes, but if it is really an Earth-type planet with a period of 1 year, wow, it's not easy. You see the completely empty domain of the Kepler detection place. So after you have other possibilities, it's for example the gravitational lensing, because in principle, okay, not in principle, it's proven that if you have the deflection of light due to a mass, you can, if you are exactly aligned, you have an increase of the luminosity of very distant objects. This was used to detect planets. Few planets have been detected by this. And this, okay, the widths of the duration of the event depend on the mass of the planet. So if it is a Jupiter, the time is typically 1 day. If it is a Earth-type planet, it's 1 hour. So you need And the amplification depends on it's very well aligned. So up to now, I do not believe they have detected any Earth-type planet like this. And most of the time, they are very distant planets. Oh, we still have a lot of work. Ah, okay.
Yeah. Mike there. Mike इधर उधर नहीं इधर.
Hello, the first question is by Dr. Rakesh Kumar Mishra. Improving planet, exoplanet, galaxy through radio telescope with use indirect observing through any radio occultation occurring data.
Direct observation. So yes, I have not mentioned the possibility to do direct imagery. This is already active, is already made. Few very clever instrumentation have been developed to do image, but it's only for very big planet, very massive planet at some distance of the stars. So it's completely out of the possibility to do images of Earth-type planet. But it's very interesting in any case, because how we can form a very massive planet so far from the star. Okay, this open different questions.
The other question is two more. The other question is Mr. Praveen K. Thakur. How will astronomical observations of exoplanets will improve if we put a big telescope on the far side of the moon?
Please give the micro to my colleague. Yeah.
Moon village.
Yeah, exactly.
Yeah, we are planning to put telescope on the moon. So there are places which are the coldest in the solar system. So you could put like a liquid mirror telescope and observe in the infrared. That's one side. But also one technique to detect planet would be through radio. Like in our solar system, sometimes Jupiter is brighter than the sun. So if you would have a very powerful radio telescope, in particular on the far side of the moon, then you don't have all this pollution from Earth people. You could detect Jupiter system around other stars, in particular when the star is quiet. And we could also search for extraterrestrial intelligence signal. So we are planning as well to have a radio telescope on the far side, also for the purpose of cosmology, but this could be also able to detect exo-Jupiter and possibly extraterrestrial signal. And for this reason, we are trying to protect the far side of the moon from other radio signal.
I will not go. Yeah, exactly.
Talking about.
Okay, the last question is by Dr. Ashok Ambasta. Is there a future human habitable colony possible on or moon or Mars? Of course, plan B of moving off to any exoplanet is not possible.
Yes, but the distance between exoplanet and here are so huge. But the story of Moon and Mars is completely different story. The light need only 10 minutes or something like this to come from Mars to here. So in some sense, it's absolutely closer. For me, the question is completely different. Do you want to live on Mars? Okay, it's not the problem of the exploration, because exploration like Apollo 11 for the moon and so on is nice, it's perfect. It's part of the dream of the people to have explored different things, like people want to go to the top of the Everest and so on. It's absolutely not because they want to live at the top of the Everest. If you are going down to 10 kilometers down of the ocean, it's not because you want to stay in the place. And for me, it's exactly the same situation for Mars. You go for the challenge to do it, but nothing more. And I completely opposite to the affirmation made by Elon Musk that he dreams that in one century we will have 1 billion humans on Mars. The worst region of the Earth are paradise compared to Mars. You have no atmosphere or almost nothing, at least no oxygen, and so on. You have cosmic ray, you have peroxide in the ground, and so on and so on. So I don't see, it's completely crazy.
Okay, we have a question over here. Just 2 more questions. Just because time is running out, a lot of people are here who want to go.
Thank you, sir, for this amazing talk. I'm Priya and I'm a student. I have a question that, as you said, that migration is not possible to other planets. Then what do you think is the future of discovering the exoplanets where habitable life is possible?
So migration of the humanity on exoplanet, certainly not. Okay, after you can do some fantasy of cosmology, okay, different, it's not physics, or at least for the moment. Migration on other planet of the solar system, I mean, or bodies like the moon, yes, it's done. And it could be, I'm very confident it will be done for Mars. But after to emigrate, what is the reason to do it? What is the reason to build a protective capsule for people living here? And I don't see the reason. And some people say, oh, if life starts to be impossible on the Earth, but this scenario, okay, a lot of things could happen on the Earth, on the climate, but always some place will be absolutely completely fascinating and good compared to Mars. No, I don't believe anybody of you will emigrate to Mars.
Thank you, sir.
Hello, sir. My name is Sankalp. And I have a hypothetical question. For example, if there is a stable binary star system and a planet is caught in the mid of those binary star system, for example, at the midpoint of binary star system, will it be able to, will we be able to detect that planet?
Help me.
Repeat again.
Sir, for example, there is a star system, binary star system, and the planet is caught between the star system. So will we be able to detect that planet?
Yes, yes. Many years ago, before we start, we have selected 142 G stars, K stars, solar type stars, known to be apparently single, without binaries. But just after the first discoveries, you have claim of planet part of binary system. You have, I don't know what is the present status, but many years ago, it was several dozen of double stars where you have 2 stars like this and 1 planet orbiting here, and sometimes maybe 2 planets like this. This exists. What is more difficult is to have 2 stars like this and 1 planet in between. So it starts to be mechanically not stable, dynamically unstable. But more recently, some colleagues have found binary stars like this and what is called a circumbinary star. So you have 2 stars like this, but the planet orbits the 2 stars. And this is very easy to understand because at the formation time, you form an accretion disk, a disk of dust and gas, surrounding both planets, both stars. And so you form a planet. Also, yes.
Good. We have a very young colleague.
Yes.
Good evening, sir. Thank you for such an amazing session. My name is Sumit. So my question is that if suppose there is intelligent life on Earth, planets like Earth, or so how would we know that there is a planet like a small rocky planet like Earth, which has life on it? Or how would even they know that a few light years away there is a civilization called human beings?
So,
On a
they
small-
The existence of human kind of life on that planet.
Yeah.
How do we?
Okay. Okay. First, I don't have any idea of that. Okay, we are not sure that only unicellular, very unicellular form of life exists. So first step, we have to find this. So after, let's imagine we find this. Okay, after the complexity of can increase and so on. But what will be the path of the complexity? Is it towards some kind of people with a brain and so on? I don't know. It's a very open question. I don't pretend it's a crazy question. Okay. For example, Christian de Duve, he was a very eminent biologist. He was convinced that the complexity towards the capability to have a brain or to have at least a capacity is completely in the path of the improvement, and you don't see any reason why other place could not have followed the same thing. So it's not, this do not signify that people will be similar to us, but we cannot exclude this. We are so far to have any basic proof or theory of things like this. So it's not for your generation to answer. It's for your grandchildren. I don't know. No, except. In 1960, some people have decided to build radio astronomer to listen to the sky and to maybe detect a radio signal not produced by normal physical process. So typically, if you have a signal produced by some television or radio and so on, it could not be explained by normal physical process. So they build radio telescope. They design extremely clever software to analyze the signal. And then after they start to search, and after 63, 64 years, nothing was detected. It's not a proof. It's not a proof. So we will see. This is a completely different approach of what I said here. You see?
We'll check one last.
Okay.
Yes, sir. Good evening, sir. Myself, I am Sadish Thambi from SPL VSSC. I'm really great honor for me to listen to your talk. My question is related to the planets, because already you mentioned more than 5,000 exoplanets has been detected. Now, I'm curious to know, because we know that actually for low mass star formation and for high mass star formation, the processes are different. So among these 5,000 planets, whatever detected, how many are actually related to the high mass stars? How many are related to low mass stars? Have you observed any difference, since the star formation mechanism is different, whether any the effect is seen on the planets also when compared with the high mass stars and low mass stars?
Yes. I believe I have to be modest, because most, if not all, the results I've given here are based on low mass stars, because the high mass stars have a lot of bad characteristics. First, they are rare, they are not frequent. So all the bright stars, the OB stars, are very far of us. It's impossible to do Doppler spectroscopy because the lines are so broad, no way to determine precise velocities. So if they are rare, the probability of truth is very, very low. So I believe it's almost nothing is known for this subject. But as it is, they are rare, okay. No, it's a limitation.
Okay, I think so. We should thank Michel for a very wonderful talk and an excellent interaction. We like to have a group photograph sitting over here. So I will request Michel now to go down and sit next to Bernard. So both are dressed well, and I will request Mrs. Michel Mayer to also join us here. We will have a group photograph. You can just come down over here. Yeah. Yeah. Catch it. Huh? Coming नहीं होता इसको लगा. Let's here inside. इसको रख लो बंद करो. बंद. We thank all those who have joined us live on the PRL's YouTube channel. And we are ending the sessions. We are going ahead with some photography. Thank you. Thank you very much for joining.